So again, in these lectures, we are going to discuss about the concept of boosting, which is one of the assembly method. As we said in the previous lectures, again, assembly learning is a powerful, as we mentioned, machine learning techniques or paradigm. We can say learning paradigm where multiple models, often referred to as a weak learners or base learners, are strategically combined to solve again a particular computational intelligence problem. So as we mentioned earlier, the core idea is that we are going to group, or we may have a group of a diverse and individual weak models that can collectively outperform any single more complex model. So again, I would say that this approach is aimed to achieve better generalization, and also, as we mentioned earlier, reduce variance and also improve robustness of the system, and also improve accuracy or increase accurate prediction. Now, by reducing bias, again, if you read articles on it, some will say yes, assembly method also reduce bias. But majority of the time, I think most likely including our textbook, reducing bias was not mentioned. So if you read some material and they said assembly method reduce bias, it may be true. It doesn't reduce bias also may be true. Because machine learning is a very dynamic field, we still learning. Long process. Every day new things come up. But we know from beginning, assembly method reduce variance, improve accuracy, also make variance reduction come to the concept of diversification or diverse. I have one big data, break it into 10 different pieces. So yeah. So that's just to recap what is okay. So we still have it here. So assembly learning again, as we said, combining multiple individual models, which we call the weak learners, to achieve better predictive performance compared to single model. And we said the two main ones are the bagging and boosting. Bagging is about para combination. Boosting is a sequential combination. Now, the difference now is here. Actually, we use this doctor analogy. A patient visit a doctor. You can see that in boosting, if Dr. A, or let's say model A performance is not good, hopefully second should be good. Third will be better than second. So it's sequential combination. We learn from the previous. So the weight will increase, kind of. Maybe it's not really clear, but hopefully it will be clear when we go through the lectures. But the para combination, as we said, everything is based on majority vote or mean. So each model, we build it independently. We don't have to know previous outcome of maybe this doctor is better doctor. We give him 90% weight. This doctor, based on his past performance, so what? That's why sequential combination can based on his past performance. So we know something already about the doctor. That's why we give him weight only 50%. Another doctor, he shouldn't even have a license. 20% good. So we give him weight only 20%. So you can see that's why it's sequential combination based on some previous knowledge. Yeah, something like that. So the goal is, so this is why I mentioned this. Now, when it comes to boosting some articles, they may say reduce bias. But we just said right now, assembly method, we don't reduce bias. But I intentionally leave it there. I left it there, so I'll bring this topic, I'll bring this discussion to the class. Previously, variance, we know about issue about variance, about accuracy, of overfitting, we know. But there was a question mark on can assembly learning method reduce bias or not. Yeah, there are some articles that they prove that yes, it can reduce bias. And some old method, no, it doesn't reduce bias. So yeah, just put. I was waiting for a student may ask a question because our last semester, I said last sem, the previous lectures, we we mentioned it about advantage and disadvantage. We we mentioned it explicitly that it doesn't reduce, it doesn't have anything to do with bias, only the variance. But here now we mentioned that no, it can also reduce bias. So I was expecting the class, maybe some of us may ask a question about that. But the only answer I can give you is that machine learning again is a very highly dynamic field. So it depends. Okay, so now let's go to the beginning of boosting now. So boosting, as we said also, and actually boosting, the main is a bootstrap aggregating. Bootstrap aggregating also, which is the bagging, we say it's a bootstrap aggregating. And the whole idea of bagging, we said what? Multiple models are first of all, bootstrap sampling. We take the sample with again replacement. And then after that, we say in bagging, multiple models are trained para, as we mentioned, independently from each other. Now, why we are trying to mention this again here, that's where we will see the difference between bagging and boosting. That's where we see the difference. In bagging, the multiple models or all the models are trained independently, and also in para, the same. Yeah. So model one don't have to know how model two did so that they can improve. No, in bagging, yeah. On a different, of course, sample or bootstrap sampling, random sample with replacement, as we said earlier. Then the final prediction is typically either we take average if it's for regression or majority vote for classification of individual model prediction. So a prime example is the random forest algorithm. As we said earlier, random forest is bagging. Use the process. So bagging primarily focus on reducing variance. You see now, focuses on reducing variance by averaging out what? The noisy prediction from individual models. Now let's come to boosting now. Boosting, unlike bagging, boosting method train weak learners sequentially, one at a time. So not para, sequence. Like in the electrical circuit, we have a para circuit, series circuit. Series circuit means the current flow from one resistor to the other resistor. Para circuit means we can have two branches. Current will flow through the two resistors at the same time. Yeah. So normally in electric circuit, we say that series circuit, the current is constant. Voltage is not constant. In para circuit, what voltage is constant, current is not constant. So why I mentioned this is that bagging boosting, kind of para and series circuits. That's why I mentioned this. I took fixes many years ago. That's why I learned electric circuit from. Yeah, so yeah, that's how oh, let's repeat. Unlike bagging again, boosting method train learners, or I'll use the term weak learners in sequential. So each subsequent or each previous model or each subsequent model is built to correct the errors made by the previous train. That's the best way we should say. So model 2 will be built based on model 1 program, model 1 performance. Let's say performance. So each subsequent model is built to correct the errors made by the previous model. So the previous model error will be based on how to improve the next model. Yeah. So this, I would say that it's an interactive process. So this interactive process focuses on what? Instances that were difficult for the preceding models, then gradually creating a stronger learner from a series of weak learners. That's where the name came from. See, you are boosting it. Booster. We use that term a lot, booster, to boost something. So boosting primarily aims to reduce bias? Now, maybe we answer that question now. So you say assembly learning, oh, doesn't reduce bias. No, it depends. Bagging does not. Boosting reduce bias because the model you build now is based on the model you built previously, how good it performed. Yeah, keep going, you know. Yeah. Yeah, so that's all I can say. Yeah, let's wait for a few seconds, then we'll move on to the next slide. Okay, so if no question. So the boosting also, we have so many type of boosting method. But we'll talk about that later on. So this is the step here. Start with initial model, often a simple one. That's a good idea. A very simple. See, previously, we just break all the training data by taking, that's why bagging, bootstrap sampling. Then we build the model para, everyone. Then we just take the average of all of them, or if it's classification, get a majority vote. By here, you can see, start with initial model, often a simple one. Train the next model to focus on data points that current assembly misclassify. See, good idea. Misclassify or struggle with. So the next model, you know, trying to get better as time goes on. So yeah. So boosting is a family of algorithm that transform weak learners into strong learners. So a weak learner, again, as we said earlier, is okay. A weak learner is a model that performs only slightly better than random chance. I think that's the term we use a lot in machine learning. Yeah. Such as, let's say, simple decision stump. Let's say decision tree with only one split. Yeah. Yeah. Something like that. So the essence of boosting lies in what is sequential and also adaptive nature. That's why we have one of the family of boosting concept is the ADA boost. Adam is adapting, adaptive boosting, adaptation. So, you know, like, you know, yeah. So let's wait a few seconds, see if any question. So that's the steps on the slide 4, as we can see. Yeah, slide number 4. See, start with initial model, often a simple one. Train the next model to focus on the data points that current assembly misclassify, if find it difficult, or struggle with, find it difficult. Then combine the new model with existing ensemble, typically by assigning weights. So that's where a good doctor will give him more weight, a bad doctor will give him lesser weight. Then we have to repeat until desired performance level is reached. So it's boosting. You know, a maximum number of models train. Or if we say we want to train up to 20, then we keep going up to 20. Hopefully the 21 will be far better than the number 1. The process, that's sequential. And bagging, para. Yeah. Okay, so if no question, let's keep going there. So that's the key component. As we mentioned what is a weak learners already. That's one of the key components. And also we said this is a sequential interactive process. Models are built one after the another, sequential interactive process. Here now we talk about the doctor. Is a good doctor get more weight, a bad doctor get less weight. Same idea here. Instant weighting. Misclassified instances are given higher weight in subsequent iteration. Basically, to do better the next time. Learner weighting. Each year, we say that each weak learner's contribution to the final prediction is weighted based on what is accuracy. So that's what's a good bad doctor. Based on how they do, we give them the weight. Let's wait for a few seconds if any question on that. Okay. Let's keep going then. So again, that's all. That's the algorithm. And we start with the core idea behind, start with initial model, train the next model to focus on data points, combine the new model with existing ensemble, typically by assigning weight. It depends. Assigning weight to depends also. Then we repeat until we get desired result we want or the maximum number of model is reached. So again, the whole idea here is sequential. Sequence will be the model one at a time. Model two will go through the process, maybe get more weight or less weight, or we treat it. The treatment that it gets in model two will be based on what model one did. So bagging, we don't have previous knowledge. Boosting based on previous knowledge. Okay, so these are the popular boosting algorithms. The common one is the first one, as we said earlier, adaptation, adaptive boosting. Then we also have the gradient boosting machine types like XGBoost, Light, GBM boost, and also cat boost. In these lectures, we are going to cover the common one, which is the ADA boost. Yeah. Let's wait for a few seconds if any question. Again, as I said earlier, if you have a question, you can ask at any time. So let's start with the ADA boost. Yeah, I can say that ADA boost is one of the earliest and also the most common one in almost every machine learning textbook or data mining textbook also. Yeah. And also most influential boosting algorithm. And primarily works by what? The keyword adaptation. So it works by adaptively adjusting the weight of a training instances, as we said earlier. And that's the algorithm steps given to us. So I'll say the pseudocode. So first we initialization. So we assign an equal weight to each training instance. For example, if there are we have n instances, it means each start with a weight of 1 by n, 1 divided by n each. Then the second we train a weak learner on the weighted data. We calculate the error rate of the weak learner. That will be the interactive training process. So for a predefined number of iteration, so that's one, actually we saw in the algorithm, the previous slide, it will stop based on, let's say, the number of models you want to create. Let's say we want to go up to 20. Or you say you're going, well, keep going until you get me the right one. Nothing change no more. Like conversion, gradient. Actually, that's what happened in the gradient concept. You know, it will keep. You reach some stage. Preview. The final result, nothing change no more. There's no improvement. So we end there. Yeah. Kind of like, or let me put it like neural network. The predictive output and real output is the same. Everything zero. And I mean everything. The error, total, let's say residual, is zero. That's our goal. We stop learning. Yeah. Then stop adjusting weight or anything. Like the learning rate in neural network. Gradient. Yeah. Descent. Yeah. So the same concept is happening here. So for predefined number of iteration or until convergence. First, we train a weak learner. How do we train it? Again, let's say, for example, on a current weight training, we start with as we said earlier, the first step. All the instances have the same weight. If it's n instances, then 1 over n for each weight of each instance. So the goal here is that I would say that on the current weighted training data, the goal is that the learner tries to minimize the weighted error. That's the first thing. So which means we have to do what? Actually, that's take us to the third step. We have to calculate the error rate. So the error rate of the weak learner must be calculated. So compute the error rate of the weak learner or the weak learner on the weighted training data. And normally this will be the sum of weights of misclassified instances. Then next we have to calculate the learner. Oh, sorry, first of all, we need to update. So calculate, then update instance weight, increase the weight, etc. Then we calculate the amount of, say, for the current week learner based on what? The accuracy. Based on the accuracy. So determine the amount of, say, for the current week learner. This value will indicate how much influence the learner will have. The influence the learner will have in the final assembly, and is we don't have the fund. There's a formula for it. We have to again calculate it. If I'm not mistaken, maybe it should be in the next slide. Let's see. But that's a step here again. Initialize equal weight for all training instance. So as we said, if the number of instances is n, we can give each one 1/n weight. Then train a weak learner on the weighted data. Calculate the error rate of the weak learner. Then we have to update the instance weight. Update it, and that will increase weight for the misclassified instance, or we decrease for correctly classified instance. Then we calculate the amount of say for the current weak learner based on its accuracy. Add the weighted weak learner to the sample. Then we have to repeat the same step 2 to 6 again for specific number of iterations. Now the final prediction, same concept, weighted majority vote. But again, here it's based on weight. Back again, we don't have weight there. And the weight will tell us the previous, we have to know the previous knowledge or the previous performance of a model. As we mentioned here, actually, update instance weight, increase the weight for misclassified instances, or decrease for correct. Yeah. Let's wait for a few seconds, see if the algorithm is okay. Okay, I waited a long time. So this means no question. So let's keep going there. So now we're going to discuss about the concept of gradient boosting again machine. So let's just read straight from the slide here, the core idea. Instead of again reweighting the data, rather GBMs fit subsequent weak learners to the residuals, that's the errors of the current assembly prediction. So that's the whole idea here. Again, so here I can say that this means the gradient boosting, I would say that it's more, I'll put it in a form that it's more generalized. It's a generalized boosting framework that can be applied to various loss functions. I think we mentioned here we talk about gradient, this loss function, neural networking concept. So instead of reweighting data instances, what GBM does is rather it will fit the subsequent weak learners to the residual or the errors of the current ensemble prediction. That's what they're trying to explain here. Now, how the process works, first of all, we have to start with the initial prediction. So start with an initial model. Example, let's say constant value, like the average of the target variable, let's say by regression. Or maybe, let's say, here they mention, or they didn't mention, but we can also say, let's say the log odds for classification. So this model has I would say has the largest residual. We have the largest residuals. Then we go through what we call the iterative process. So in the iterative process, we are going to calculate the pseudo residuals. Calculate the pseudo residuals, which is here. They are the pseudo residuals. So calculate the negative gradient of the loss function with respect to current predictions, which we call the pseudo residuals. So again, we calculate the pseudo residuals, which means for each training instance, again, we calculate the pseudo residuals. And this will be or I would say this is very essential. essentially the negative gradient of the chosen loss function with respect to the current prediction of the ensemble. Again, here we are kind of converging gradient concept. Let me wait for a few seconds here, if any question maybe. Normally, this is where it's a student from previous lecture student asks questions. Or let's keep going. So if you have a question, you can just speak, then I'll again keep quiet. So here also, for example, after that, we have to find, let's say for a square error loss in regression, the pseudo residuals are what? Simply the true residuals. And what will be that? The difference between what? The predicted and the actual Y value. So yeah, so kind of use gradient convergence we said earlier. So in B, the next step, we are going to train a new weak learner. So first we calculate the pseudo residuals. Always residuals will be the difference between residuals normally will lead us to the loss function concepts also. The difference between actual predicted and kind of. So next we train the new weak learner. So train a weak new example, let's say decision tree, to predict these pseudo residuals. So the tree learns the patterns in the error. Then the next step we are going to add to ensemble, which means here now we had a prediction of this new weak learner to the ensemble's current prediction. So this addition typically it will scale by learning rate. See, or this is where it can be shrink, or shrinkage the parameters, which helps prevent overfitting by doing what? Controlling the step side. Again, if we understand the concept of gradient descent, the same way it's working here. I mean, yeah, the same way it's working, the same way it is here. Yeah, that's what we are trying to say. Let's wait for a few seconds. So first we calculate the pseudo residual, train a new weak learner. Then we have to add to ensemble. Then we have to update the predictions. So these ensemble predictions are updated based on what? The new weak learner's contribution, based on previous contribution of the weak learner. Then we get the final prediction. So the final prediction is the sum of what? The initial prediction and the scale prediction of all the subsequent weak learners. Yeah. Let's wait for a few seconds if it's okay. Again, loss function can be used. So can use various loss function, example, square error for regression or log loss for classification, etc. Gradient descent, no, gradient boosting. Well, let me say gradient boosting. But neural network, we talk about gradient descent, loss function. The same idea here. Yeah. Okay, so if no question, I think we kind of finish in this section. We almost finished with the algorithm. Again, GBM or gradient boosting machines. So what are the advantage of boosting? Well, I think here we're supposed to mention bias here now, but let's see. The first one is high accuracy, handle complex relationship, versatile robustness also. This is good for both classification and regression. Then also feature importance. Most implementation provide insight into feature importance also, they said. But I also said robust to outliers also. Robust to outliers with careful tuning, especially for the GBM. Very good. So we know why very sensitive to noise. Some advanced GBM variants, where, for example, cat boost, yeah, and then proper or with regularization. We didn't talk much about regularization methods, which can also be used, I think, in neural network. Regularization can make them more reasonable, robust. Accuracy is very good, same as bagging, high accuracy. Okay, so if no question, let's move on. Let's see the disadvantage. Prone to overfitting. That's almost opposite to bagging. I think we say bagging. Not I think, sorry. If I say I think, like I'm not sure. Uh, Bagging, we say overfitting, solve overfitting, but I say boosting, no. Yeah. So prone to overfitting, especially if the number of iteration is too high or the learning rate is too small. Yeah. And also we say sensitive to noisy data and outliers. So now because boosting algorithm interactively focus on hard examples or errors, and they can be disproportionately affected by noisy data or outline data, very large, small, which might be again repeatedly lead to misclassify, or have a large errors, or let's say have a large residuals that can lead to a large, causing the model to learn from them rather than ignoring them. We don't want the model to learn from noisy data outline, especially outliers. Yeah. This can lead to misclassify, so that's disadvantage, sensitive to noisy data outliers. And also computationally intensive also, computationally intensive. So let's wait for a few seconds, and also less interpretability. I think this is the same concept with bagging also. Yeah. Okay, so if no question, let's move on. So these are some few things we can mention, something we call the hyperparameters, tuning and etc. So again, yeah, we can say that I would say that if hyperparameters, hopefully we understand the concept to tune. Yeah, for example, or I would say that effective use of boosting require a careful tuning. I think same like a neural network, the weighting each epoch, learning rate, same thing here also. So initial weight for each instances, we have to tune. We have to make sure we get a careful here. So some examples as given about under the upper parameters. Number of estimators, iterations, very important. Again, compared to neural network, also number of epochs, initialization of the weight, etc. Learning rate, very important. So learning rate here, they say controls the contribution of each weak learner. So very important. Because this parameter control again the contribution. Same as neural network concept. So smaller learning rate means each tree contribute less, require more and estimators, but potentially leading to more robust model. Again, the key word is potentially, hopefully, to lead after we increase. Also, the maximum depth, very important. Like example would be like decision trees, the length. Subsample ratio also. And last will be feature subsampling. Normally, the feature subsampling parameters control the fraction of features. We know features are the column features, like I'll say columns. Random sample when building each tree at the different levels. At the different levels. It can be per tree or per split, etc. And this actually will lead to diversity. introduce diversity and reduce overfitting. Yeah. Tuning out the features of sampling. Okay, so if no question, let's keep going or wait for a few seconds. Good. Okay, so application of boosting, we can say same as bagging. Use the credit scoring, fraud detection, search ranking, medical diagnostics, also image recognition, customer churn prediction. Yeah. Then lastly, let's compare the boosting versus bagging. So I would say that it's very helpful to know the difference or distinguish boosting from bagging because both are, I would say both are powerful assembly method, but fundamentally there's difference between them, difference in the approach, yeah. But they are both based on the advantage we can see of both of them are powerful. So we have some features, and then we have bagging, then we have boosting. So example of bagging, they say random forest, other boosts, the most common, or the GBM we went through, gradient boosting, we went through. So first, the approach, as we all know, bagging is para, whereas we say boosting is sequential. So dependent model, which means previous model performance can determine the next model based on weight adjustment, etc. But we know in bagging, it's para. The models, they are all independent. They can be created at the same time. That's why they are para. Okay, yeah. Then the goal, of course, yeah, now this is where, yeah, this is very nice here now. See, the goal of bagging is to reduce variance. The goal of boosting, reduce bias. Then we focus, of course, diverse models for bagging we mentioned. And also boosting based on the previous, again, correcting errors of previous model. Then weak learners can be strong, often compressed trace, must be weak, often shallow trace. Training speed, okay, faster because it's parallelizable. Of course, sequential slower because one after the other. Interpretability, moderate. I thought both of them should be low, but they say bagging is more moderate. Boosting is low. Overfitting, yeah, less prone. Now we can see bagging less prone to overfitting, but more prone. If the last session we talked about the tuning of the hyperparameters were not done correctly, that can lead to big overfitting issue. I won't say big, that can lead to overfitting issue. Yeah. Yeah, let's wait for a few seconds if any question. Okay. So that's the conclusion we have here. Boosting is powerful. I would say same as bagging. Why choose boosting or bagging may depends on the type of problem you have. Yeah. So boosting stands as a cornerstone techniques in the field of machine learning. Uh, Renowned for its exceptional predictive accuracy. I would say same as bagging. Its strength lies in what? Adaptation, sequential, one after interactive process, where the weak learners collaborate to build a powerful overall model by continuously what? Learning from and correcting the previous error, why it demands careful hyperparameter tuning, also as we mentioned earlier. Now, this hyperparameter tuning also can lead us to overcome overfitting issue. And also because of that, also, as we said, boosting in general, computationally intensive, same as bagging, or computationally very costly. Okay, so that's all we can say. If no question and also last one, it's a variable tool in any data scientist arsenal also. I think the same thing is said in bagging also. Yeah. So that's an example for boosting. Again, this came from the data mining textbook again. So I brought it, but I like the way they write this step down. So they say the analogies here also consult several doctors. Now, based on the combination weighted diagnosis, weight assigned based on the previous diagnosis accuracy of each doctor, we may make our, Previously, the same doctor, no, it doesn't matter how good they are, how bad. Just majority their decision or average their decision. But here we are using weight, so weight assigned to each training tuple. Then after classifier MI is learned, the weights are updated to allow subsequent classifier, which will be MI plus 1. The next one, to pay more attention to the training tuple that were misclassified by M1. See, so based on the previous learning. Then the final M star combine the vote of each individual classifiers, where the weight of each classified vote is a function of its accuracy. Now, if boosting organic can also extend it to numerical prediction. Comparing to bagging, boosting tend to have greater accuracy, but also risk overfitting the model to misclassify data. Then bagging overfitting problem is solved. Both can solve high variance problem, but high variance problem is more bearable to bagging, because we divide the data and we do it in para. So we mix all the data together. Here we build one at a time, the model, based on the previous model work, performance, performance or how it work. Then we may know, adjust the weight. Okay, so that will be the conclusion. Let's wait for a few seconds before we stop the recording. Okay. Stop the recording.